If I have this, it's going to be okay for me to have. Okay, so like I know that I'm gonna see.
Okay, so we are going to make a little mathematical reinforcement towards the subject of Fourier analysis, which will be the last subject of the course, and this is quite a heavy subject. So I wish to have a fruitful reinforcement, which I hope will give you some clue and more understanding during the next classes of Izar and mine. Okay, so first of all, I just want to talk about a few of the features of the functions of sine and cosine. Okay, so first of all, sine and cosine are a periodical function, which means that we can look within each sine between two peaks or two troughs, and this is called the period of this wave. So please note that most students are quite confused about that when you want to count the number, for example, you're given with a kind of a draw of the signal, and then you want to count how many periods do you have in that signal. So know that you need to have a full period, meaning that you can take either the distance between two peaks, two troughs, or just look when are you going back to the same spot. So for example, here, when we look at the spot over here of 0, this is the grading spot, right? So if I want to see a full period, so I need to take from 0 over here, go down and up again, and only then I'm back to the 0. So please note, because there are a lot of students which say, okay, this is 0 and this is 0, so the period is just between the two of them, but this is not true. This is half of the period. Okay? So this is the main thing that we use in sine and cosine. So this is why I started with it, because all the idea behind Fourier analysis is that we use the fact that there are things that are repeating themselves on in the data and so on, and we use the sine and cosine as a kind of approximation to this periodicity. Okay, and we add to it another important feature that we will talk about, which is the amplitude. And the amplitude is how high does this wave fluctuate? It fluctuates. Okay? So how high does it fluctuate? So we take, we are not taking from the trough to the peak, but we are taking from 0 to the peak. So please note, for example, if you have a DC shift, which means that you take all of this sine upper using the DC, so then you can look at the distance between trough and peak, and you need to divide it by 2. And this is the amplitude, okay? Great. Okay, next thing that I want you to be encountered with is a very, very important feature of sine and cosine, which is called phase. Anyone knows what phase means? Again, another very confusing term in this field. Great. So a very good way is to talk about the shift from sine to any other way. So for example, the shift from sine to cosine is like taking the sine function and moving it, shifting it pi over 2 to the left. Okay, so this is one way. Another way for phase shift. Another way to explain phase is how do you start the system? Where does this system start from? Because, for example, here we are commonly using sine and cosine when the x-axis is time. So you can decide what is time zero. What could be time zero? It could be, sorry, I'll shut it off. So time zero could be the second that I started the recording, but this is quite a random, right? So another way is to say that where time zero is the phase, okay? Is that clear what I said? So I can say that I take this axis and I move it. I say that I began, now the zero is here, for example. And where I start, this means what is the phase of my wave. Okay? Where does the y-axis? Another possibility is that we say that we have a specific wave in our data, and we say this is our sine wave. This is our how is it called? Also in EEG, that you have a repair. Okay, so this is the phase of phase zero, and then each other signal in relation to this signal is the phase shift. Okay? And the fourth way to explain it is by saying that the phase is the movement across this across this function. So sine of x, here it's zero, but then when I add the phase, I move along the signal. Okay? So there are many ways to understand the meaning of the word phase. And I wanted to encounter you with this idea because many times when we say phase, it will mean different things. It could either mean the shift between two signals. For example, when we will talk about coherence, or it can be the related where I am on the graph. Am I here or here? At what phase I am? Okay, and this is, for example, the Hilbert transform that I will say a few words about it. And it could either be where is my zero? And this is, for example, in some of the studies that in the study that you are going to have in your project. So it's where is the zero? This is the phase, right? So it's not that simple. Okay. Okay. Sorry for the level of the resolution. So another feature that I want to talk about is power. And when we say power is in relation to the amplitude. Where is it given from? So we say that energy, kinetic energy, do you know that? That it's half mv squared, right? This is the definition for energy from physics. And when we have a wave, in a wave, the velocity is the amplitude multiplied by by omega. Omega is the angular velocity. Okay? And this is why you see over here that the amplitude is inside something which will be squared. And the reason that they give you the direct formula is not that they want you to remember the physics behind waves, is that they want you to understand that every time we say energy, it is in constant relation to the amplitude, to the square of the amplitude. So when you're asked, for example, when we will do something that is called power spectrum, when we say power is the square of the amplitude. So far, any questions? Okay. Okay. Great. So just two more terms that we're going to use, and then we'll go on to the Fourier analysis. Do you know what does even and odd functions mean? Right. So what does it mean? Please, Kanepi. Right. And what we see here, we have this blue and green functions. Which one of them is odd and which one is even? The blue is odd, right? And the green is even, which means that if it's like a mirror, if the y-axis acts as a mirror of the two sides, this is an even function. And if it's a mirror that is flipped, okay, over here, I can flip it, and then it's a mirror. Do you see that? In such a case, this is an odd function. And why is this important? Because look again at the sine and cosine function. Which one of them is the even one? The cosine, right. And which one of them is the odd? The sine. And why do I say something about that? Because when we are going to use Fourier transform, Fourier series is kind of taking any possible function and takes the even parts of that function and the odd parts of that function and writing the even parts with cosines and the odd parts with sine, okay? So this is like on one leg, the basics of the Fourier series. The fact that any function is given by sums of even and odd functions. So this is why we can use it when we want to create approximations using sine and cosine. Okay? Okay, and last thing that we are going to talk about, and this is more of a mathematical definition, okay? When Izar will show you the direct formulas of the Fourier transform, it will show you a formula that is using E powered by I theta, okay? And some of you might not be familiar with this kind of writing. What does that mean? So Euler's theorem says that there is a relation between E I theta, this function, and these two functions, so that E I theta is cosine of theta, plus the imaginary part I sine theta. Okay? And why do we use that? Because now you understand that we can write, each time that we write cosine, we can write something with E by I theta. And each time we write I sine of theta, we can again write something with E I theta. Okay? Do you know the reverse relation between them? Okay, I'll show you. So, for example, if I want to have only the cosine of theta is, for example, 30 degrees, which in radians, that's pi over 6. Everyone knows what radian means? Okay, radians is another way, instead of using degrees, it's a way to say what part of the circle is represented by the degrees. So that 2 pi equals 360 degrees. Therefore, pi is 180. And when I take 180 divided by 30, this is 1 over 6, right? So this is why pi over 6 is 30 degrees. And of course, we will use only radians. Why do we do that? Because radians are real numbers, while degrees are only degrees. This is like, instead of talking about meters, you have something that is a pure number. Radians are a pure number, so it's easier for us to create functions with it, and not with degrees. Okay, degrees is only for circles. But sine and cosine we have like here, when we have this function like here, so it's not like 0, 180 degrees and so on. So it's 0, pi, and so on. Okay? So let's go back over here. So I was asking if you know the transformation between cosine and the imaginary and the Euler theory. Okay? So we know that E by I theta equals cosine of theta plus I sine of theta. And E by I theta minus I theta equals cosine of minus theta plus I sine of minus theta, right? The only thing that I did was just writing here minus instead of plus. So what is cosine of minus theta equals? It is an even function. Therefore, this one equals cosine of theta. Great. And I sine of minus theta equals sine is an odd function. Therefore, it's a minus sine of theta, right? So this is minus I sine of theta. Now, what happens when we sum up the two of them together? So if I take E I theta plus E minus I theta, this one equals to
2 times cosine.
great. 2 times cosine theta. Therefore, we can deduce that cosine of theta is E by I theta plus E by minus I theta over 2. Right?
Yeah,
Yeah.
then would it be possible to show the rest of the bottom of the board?
And sine of theta is what happens when we reduce between them. So what happens when we reduce? So we had E by I theta.
Yeah, maybe they don't see. Yeah, I know.
Oh, sorry. There you are. So E by I theta minus E by minus I theta. I don't hear it. I should have heard it. Okay, strange. What happens when I subtract between them?
So since I sine theta equals same as the cosine is equal to 1.
Right, so this one equals 2I sine of theta, right? So sine of theta equals the subtraction between E by I theta minus E by minus I theta over 2I. Okay, and this is how I can isolate the cosine and the sine from the Euler theory. Now, what exactly does that mean? The plus and the minus, right? Sorry, no, of course. So you see that the cosine and the cosine, I just took the two functions and divided by 2. So this is why we say that the cosine represents the real number of E by I theta. So if this is an imaginary number, it has the real part and the imaginary part, right? So the real part is described by cosine theta. And the imaginary part by sine theta. So if you understand that, so let's say, for example, that we have the number 2 plus 4i. Okay, this is the number, an imaginary number. How can I write it with sine and cosine? How should I do it?
Like cosine 2 plus sine.
Right, so 2 should be the cosine. So the first thing that I'll do, oh, sorry, I forgot to say that of course this should be equal to 1. So I'll just write here something different. Because this is on the You see here, everything is only for 1 and I. So maybe what I will do is write it like this: 1 over the square root of 2 plus 1 over the square root of 2 of 5. Okay, the reason that they pick this number is that when they are squared up and summed together, they equal 1. This is why these are the strange numbers. So I need to write it as cosine of theta plus sine of theta I, and theta equals which angle has the same for cosine and sine, same number for cosine and sine, 45 degrees, which is I over 4. Okay. So now I can represent any number by a specific theta. So this one is represented by 45. Okay. So I don't want to go into too much details into the field of imaginary functions, but this is the basics, this field. The fact that we take the Euler theorem, and what I want you to remember from that is when you see this I, P by I theta, it's like writing cosine and sine, where the cosine represents the real and the sine the imaginary. Okay, so this is what I want you to remember. The transformation between each possible imaginary number and the trigonometric representation. Okay.
You knew that it's pi over 4 because both of them were equal.
Yeah, and another way, of course, is to just to calculate it with your calculator.
Okay.
Okay. Great. So far so good. All the basic features are clear. Right. So now let's talk specifically about Fourier. Okay. So Fourier series, it's really one of the most important and remarkable advances in across humankind. And the history of how it was discovered, I think it's not that important. It was a mathematical problem that and a special ODE that had no solution, or it wasn't like an ODE. It was a partial differential equation that didn't have a solution. And then came Fourier, and he offered how to solve it using a series, a special series that is written like this. Okay. But let's first understand it graphically. So what is the idea behind the Fourier series? The Fourier series says that you can take every function and write it as an infinite number of sine function and cosine combined together. So what you see over here is that we have this square wave. And for this square wave, what we did is the following. We took the sine, and then we added to the sine another function, and we got this yellow line over here. And then we added another one and another one until we have something which is really similar to the square itself. Do you see that graphically? And we can do it also here. If we have a straight line, this is called a sawtooth plane. So we have a line, and also on this side we have this orange. Do it with the mouse so the Zoom can see it also. So we have this orange line, which is again, is it the sine or the cosine? This one is the cosine, I think. And then we add to it another function, which is another sine, and then we have this yellow. And then we had another one, which is this green, and another one which is this blue, okay? In a minute, I'll show you this in this very, very nice simulation. And we can do it also with a triangle way and a semicircle, okay? So we can take really every possible function and just start adding sines and cosines together, one to the other. And by so, when we do it until infinity, we really have the same function, but written with sine waves. So this is really a revolutionary idea that you understand that each function or each signal contains sines and cosines that are kind of approximating these signals in a very strange way. Okay? In a minute, we'll go into details into this formula to understand it. And I want to show you a very nice simulation that I like. So, okay. No, you don't see it good. 1 minute, the zoom is. Okay. Great. So I'll just double check that the zoom see it also. Yes, okay. So I'll start by clearing everything, and I want to show you what happens when I start adding. Can I make it even smaller? No, that was too much. Okay. And what I'm going to do is just starting adding the sine function. So, oh, I forgot to say something about frequency. So what you can see here, that each dot has a number in it, right? Do you see that? You cannot see like this. 1 minute, okay, and I'll just take it here and please work. I try to magnify it, but not. No. I try to magnify it, but the side of the screen, the resolution is not good, so I cannot do it automatically. If someone is good with that. Okay. No. Great. Yeah, this one looks better. Okay. So what we see here is that we have all the signs over here, right? And inside each sign, we have a number, and this number represents the frequency. Now, I forgot to say at the beginning that there is a relation between the period and the frequency. They are opposed to each other. So frequency equals 1 over the period. Therefore, if you see here, for example, sine of 2x, that means that you have 2 periods within 1 second, okay? Or if you see here 8, this means that you have 8 periods within 1 second, okay? So we have here the sine and the cosine, and we can start just by having one of them. So you can see each time that I'm with my mouse on the specific function, it is colored with yellow. And then we can start adding signs to this function. I can have like something higher, something lower, yes.
First you set frequency and then you set periods for the number inside the.
So the number over here. So for example, 4 is the frequency. What does the frequency mean? how many periods I have in 1 second. So if I say here 4x, that means that I have 4 periods within 1 second. So the size of each period is 250 minutes. Great. Okay, so what I wanted to show you is that I can start working with this nice simulation that I have here, the first sign, and then I can start adding another sign. So you can see this is the second sign function, and this one is the first. And they are, when they are added to each other, they create like this very special and unique pattern. So, for example, if this is 1 and this was 2, let's say.
Why is I don't understand why the frequency, what's the frequency number represents?
The frequency number represents how many periods you have in 1 second.
But I don't have,
Here, take the x as a t. We always
no,
have
I
it. As
understand that, the number above, number like 5,009.
in a minute, I'll make you hear that. In this nice simulation, you can also create music using this sound. So it tells you what sound it's gonna play.
Okay,
And the relation between the sounds or the relation between the sign functions.
okay.
Okay, so for now, don't look at the hertz. Okay, only at the signs. What is written inside the sign? Yes.
Just curious to know what is the difference between the heights that you.
So this is the amplitude of each one. So for example, if I have a high amplitude of this slower sine function, so I see that the main frequency that this is the slower one. And then I can add on it the one which is faster, but this one has a lower amplitude. But if I change the relation between them, so I can have here a much smaller for this one, and this one will be the maximum, then I see much more stronger the frequency of the higher, not the frequency, much more stronger in my signal, the higher frequency, right? Okay. And then we can start playing with this built-in function. So for example, how does a triangle look like? So we can see here the idea that we have this this cosine function, and we added to this one, and then this one even smaller, and this one even smaller, so that we are skipping within every 2 frequencies, right? You see here, frequency, no frequency, frequency, no frequency. And the relation between the frequencies is not that they're equal, they have a relation between them. For example, this one might be 8 times smaller than the previous one, and then smaller, and then smaller. So the relation between the frequencies is just given by the Fourier series, how to calculate the relationships between them, okay? Let's see another example of the sawtooth. So what we see here in the sawtooth is that we have this function over here, and this one, when it's minus, it's a cosine, okay? So it could have either this one or the same cosine here flipped above. When it's minus, it just means that it's cosine. So we have a sine, cosine, sine, cosine, sine, cosine, sine, cosine. And the size of each one, again, is calculated by the Fourier series. The size is the amplitude, okay?
How do you know which ones are cosines?
The one which are negative here. It's just in this simulation, I forgot to say, when it's negative, that means that it's a cosine.
Wouldn't it? Isn't it not just the sine of 180 out of phase rather than cosine of just 90 out of phase?
So let's see, maybe you're right. So this one is this one, and then the other one. Yeah, you mean like they're exact, wherever there is a trough, there is a.
Yeah.
Yeah.
Minus it's pi, and the shifting is pi over 2.
So it's pi and not pi over 2. Yeah, I think you are right. Yeah. Yeah, okay, thank you, Esther. Yeah.
There's no cosine.
So no cosines in this one, right?
Yeah.
But you can write each sign as a cosine by just phase shifting. Yes.
Can you repeat what's the difference?
So the positive is that it will have in the zero, it will decrease. And in the negative, it's phase shifted by 108. It's not 180, are you sure?
From the zero, not from the left edge, from the middle.
This is the zero,
Yeah.
so this is a sign,
Going down.
and this one is, yeah, you are right. Great. So this one decreases wherever the previous one was increasing. So they are phase shifted exactly at 180 degrees, meaning pi degrees. No degrees, pi. Okay? So you can see this really nice idea that they are shifted one after the other. And here again, we can see the square. So for the square, we have, we have 1, and then we don't have 1, and then we have 3, and we don't have 1 at 4, and 5, and so on. So it's only the odd numbers of frequencies, and the size of each one again is calculated by the Fourier series. Okay, and here is, for example, a noise. And what is defined with noise? When we said white noise and so on, so noise is that you take all the possible frequencies and you just kind of randomize the amplitude of each one, but you have all the possible frequencies. And now, do you want to hear one of them? I won't do it too loud because it's really awful. Okay, so here's, for example, this is a sawtooth. I don't know if you hear it. Turn up. Right. So this is sawtooth. And this is triangle. Much more, do you hear it? It's much more clear. It's pretty amazing that our ear is built upon this idea that it takes out the different frequencies and it hears the relation between them. So the dyscoplia is built in a way that you can hear the exact frequency within each part. Okay? So, and here, this is noise. You hear it. You hear that it is a noise. Sorry. And okay, you can play with it. I think it's a really nice simulation to better understand this idea. So this is about the idea of the Fourier series. And now let's look here. Do you see it good?
Yeah.
What is written here? So we won't use this formula, but we need to understand what we have in this formula, because in a minute we will see the Fourier transform, and it is based upon this idea. Okay, so what does the Fourier series say? It says that given a function f, now you can write this function as 3 parts: a DC shift, meaning that where is this function in relation to the zero? Is it exactly crossing the zero, or is it above it? Okay, so this is A0, the DC shift. And then you have bunch of cosine functions and bunch of sine functions that the size of amplitude of each one of them is computed by these 2 coefficients. Okay, so you have here a coefficient of each one of the cosine and the sine, right?
For the amplitude.
Yeah, the amplitude of each one. So each one of them is 1, and then you want to know how strong they are. So you compute this AN. Okay, and what we see over here, this is the infinite series. What does an infinite series mean? That you have an infinite sum of functions. As we saw in the simulation, you could have infinite numbers of frequencies, and you can add them together, right? Or you can put sines and cosines in a mixed way, right? This is really, so this is the basic idea, okay? So, and how exactly are these coefficients are calculated? So this is again the Fourier theory. And we don't need to remember that, but we just need to know that each one of them is a kind of an integral of the function and a cosine function, okay? So here, these are the frequencies of each one. I think this is the main thing that we need to understand, okay? Any questions so far? I heard a really nice anecdote about Fourier, that when he came with this idea, nobody wanted to publish it because they say that it is not, that some of the mathematics are not fully clear. Okay, so they said, it's a cute idea, but we cannot publish it because there are some restraints here that are not fully clear. So he went back and he tried to do some new things, not really important thing, like the fact that there are, for example, this, how do you calculate this? You just take this line and you copy it again and again and again. And then when you copy it, you have here a non-continuity. And the fact that you have this non-continuity and the sine function does have a continuity, this is what really got all of this mixed up. And they say, until you solve this problem, you cannot publish it. So it took him like a few more years and then he published it. And again, one of the most important findings in the humankind, which is relevant for everything, for engineering and physics and biology and neuroscience. Everything uses this beautiful idea. Okay? Right. So what are we going to do in the course? We're not going to use the direct Fourier transform, Fourier series. We're going to use the Fourier transform. What does that mean? So I'll just reopen it. Over here. So when we use this Q simulation over here, right? So I told you that you have this function, and then you can write the frequencies of each function like this, right? So one way to describe the relation between any function on the X series and this relation of the frequencies is by saying that you have a new domain. Over here, the X-axis is frequency, right? Do you understand why? Here, the X-axis is time over here. And here it is the frequency. So you might say that what we are doing using the Fourier series is that we are transforming from one dimension to another one. From the dimension that we have the function itself to a new dimension that we have the frequencies and their power in our function. Okay? And this is the Fourier transform that we see over here. What? Okay. So what does the Fourier transform say? It's saying, take your signal and multiply it by cosine and sine. We remember that this represents cosine and sine. And I brought here just from the internet. I didn't really check everything up. So J is like I, okay? And omega is the frequency that you see here. And T is the time axis. Right, and we can see here the Fourier transform changes the signal from time domain to frequency domain and back again. So what does that mean? That if we have this signal over here, and we have full recording of it, and we take this full recording, we can transform it to, this should be the frequency domain, oh no, still the time domain, to bunch of sine and cosines that are just summed up together, right? And now we can take the size of each one of them and write them as we saw in the simulation. And this is what you see here. So if we have, again, this signal, now we took all the frequencies, we use the Fourier analysis to say which frequencies do we have in this signal. So we have all these frequencies over here. You see, we have the blue and the green and the red and the orange and purple and so on. Now, which one is the biggest? Which frequency? The blue. And which one is the smallest?
Light blue.
The light blue, the CI, yes. So what we can do now is just saying, okay, let's look at the blue. What is the frequency that we see here? So the frequency is 1/t. 1/t. We have a full period at a specific.
When you said bigger before, you meant the amplitude of
The amplitude.
frequency.
Exactly.
Okay, because they're both like, okay.
Yeah. So the amplitude of the Fourier, when you use the Fourier transform, the amplitude of this one is the biggest and this one is the smallest. And this one has a full cycle within t. T is a number, 1 second, for example, okay? So this one has a full cycle within 1 second and has the highest amplitude. So let's write its number as the highest one over here. Okay, in a minute I'll say what this number is. And now when we look at 2/t, how many waves do we have exactly that have 2 cycles within 1 period? We have none, right? You see this one is empty
Can you repeat that?
here. So we see how many cycles do we have within T. So we have here, this one has 1, this one has 3, this one has 4. If you remember from the simulation that we had these jumps, 1, 3, 5, 7, and so on, only odd numbers, right? So this was the square signal. Okay, do you follow so far, or is it too much?
More or less.
More or less,
Not too
okay.
much, not too much, but I just don't get, when you say how many cycles, are we referring to which one of the cycles?
Let's see it again. I think the simulation was a bit more clear for you. Okay, so let's go back to the simulation. Oh. Okay. So where is it? Sorry, I took the wrong one. What? Okay, so it's this one, right? Now, what are you doing? Okay, so let's see here again the square. So we have this sine of x. So here is the 0, and let's say here is 1 second. So we have full cycle within 1 second. Now I look at the second one. The second one, here it's 0. Let's add it so we can see how it looks like. So the second one from here to here, you have 1, 2. So you have 2 cycles. But this one, for the square root, the square wave equals 0. Okay, you don't have it. You don't have this frequency. So you have at 1, at 3, 5, 7, 9, and so on. You have only frequencies which are odd. Okay, so what I want to do is to take this a square wave and write these frequencies as my function. Okay, and this is what the Fourier transform does. So when we take it back in here, so we have these signs coupled together, And then I take only the related frequencies and I write them in the frequency domain, where my x-axis is frequency. This is the difference. And the height of each one is how strong is this component in our signal. And this is what we see here. So this one is the strongest, and then you have lower and lower and lower. And you can see that there is a relation, a function which relates between them. Okay?
In the frequency domain, the amplitude is the actual amplitude in the
Yeah,
time domain.
yeah. And what you see here, Bn is, it's taken from here. This is the Bn. It can be like directly computed. And then you can write it here. Now, this is again the mathematical idea. What is I will speak with you about tomorrow is how you take this really nice idea and then you try, you start when you are computing it. And you have the fast Fourier transform, which is a way to create the Fourier transform using the computer. And remember that each signal in the computer is digitized. So we'll talk a bit about these digitations. They create a lot of problems when you're doing Fourier analysis. But I want you to go from here with some of the basics ideas that you can describe any signal as bunch of sines and cosines, and the Fourier transform gives you their amplitude. What kind of picture don't we have in the Fourier analysis? What don't we know about the different
Maybe phase.
exactly. So we will also talk about phase relation, because sometimes I don't know how much Islam will talk about it, but I will surely talk about it, the relation of phases. So for phase, we have a different transform. This is called the Hilbert transform. And using this transform, it's about the same idea, but instead of an x-axis of frequency, we have an x-axis of phase. Okay? And this will be used for a different type of signal and data analysis.
But how do you provide the phase to the amplitude? Different frequencies have different phases, right?
Yeah, so you don't have it here. So what you understand now, that if you have this signal, in a way, you have 4 dimensions. You have its y-axis, right? The x and the y. So this is the time, and this is the signal itself. You have its frequency, you have the amplitude of the frequency, and you have the phase.
Yeah, but what, I mean, you were talking about the phase, right? And
Yeah,
you said that in the end of the transformation, you have a graph of the frequencies and what is the y-axis of that?
the amplitude.
The amplitude.
Yeah.
So how can we correlate the phases to the frequencies? I mean, each frequency
Yeah.
has different phases, right?
So to understand that, we'll go through something which is called filters. And then we filter the signal into
Okay.
a specific frequency, and for this frequency, we calculate the.
Yeah.
But this will be within 2 recitations from now. Okay? Yes,
The function that describes the amplitude that you said,
yeah.
uh,
Here,
yeah, is it like, do we write it or use it, or is it just to?
you compute it. I gave you like the full mathematical formulas, but in this course, you don't need to write anything. What I think you don't need to do anything analytical, or if you do, it's like a really simple thing, not like this one.
You know, but in general, to understand this, how like part of the.
Yeah, so they are computed by this formula. So if this here L is the period, and you take the function, you multiply it by sine of a specific frequency, you make an integral, and then you have the power. Okay?
Bn is the right?
Yeah. It's the, yeah, it's called the amplitude, yes. Or sometimes it's the power. The power, which is what is the relation between power and amplitude? Great. So please remember that. So just a very, very small last thing, because this is where kind of we will start in the recitation. So this is the exact Fourier transform. You can go from the real function to the frequency domain. You see here, the x-axis here is time and here it's frequency. Or you can have the inverse, okay? It doesn't matter the formula, just note the two axes that you have here. And these are the transformations. So if you have a signal, which is a cosine wave, this will look like a delta function in the frequency domain. Okay, I just used all the notations. It could be T or F, everything, okay? Here it's omega. Omega is also frequency. Just, I know, start to get ready for that. Now, if we take a square at the frequency domain, and we use the Fourier, the inverse Fourier transform, we have a very important function called sinc. We will talk a lot about this function. This is very, very important in relation to filters. Okay, it makes a lot of problems in signal and data analysis. So just remember this relation. And here you can see, for example, that the Gaussian looks the same at the time domain and the frequency domain. And here, this is an exponential, and this one becomes really similar to a Gaussian, which is called the Lorentzian in the Fourier transform. But here are the main functions that we are going to talk about. Okay? Yeah.
I just didn't understand the relation. So the signal.
So if you take a signal that looks exactly like this in the frequency domain, it will look like a delta function.
After we use Fourier transform.
Yes, yes. And if you're going the other way, if you have a square, how will it look like in the signal domain? It will look like a sinc function. And please remember it. Okay. Questions? Yes.
In the previous slide, we saw that the amplitude was Bn.
Yes.
So that means that all of the signals were sines, because I remember B was for sine and A was for the coefficient.
So the coefficients are sine multiplied by the function.
Yes, so the other signals are just sines.
It's, yeah. It could be either sine or cosine. In Fourier transform, we don't know. We just know that this is the frequency. This is all that we know. Because they can be convertible in relation to the phase. And for this reason, after we will understand better the frequency domain, we will start talking also about the phase. Yes, more questions? Great. Thank you for coming. Yeah.
What's the difference between Fourier series and Fourier transform?
Okay, so Fourier series is that you need to have an infinite number of cosine and sine, and you have all of them. But in the Fourier transform, you plot them into a new domain that the x-axis is the frequency. And another thing that we will do in this one, you must have a function. But as I will talk about it, that the Fourier transform doesn't have to take into it a function, it could have any signal. And it can compute the Fourier transform of this signal. Signal might not be a function, right? Function is that you have a rule. You know that, for example, f of x is x squared, and then you go on from here to calculate in the Fourier series, and by the Fourier series, you have the Fourier transform. But the signal could be also something like that, right? And it's not a function, it's not like a pattern, but still you can take it and perform a Fourier transform, a special kind of Fourier transform. And by this, computing all the frequencies that you have in this signal.
So after having done the Fourier transform, we finally end up using anything, right? Which is the sum of.
You kind of, what we're doing is that we use parts of it as if this is the function and this is something that I believe we will talk about it a bit more.
So in Fourier series, you need the whole function, but in Fourier transforms, you just split the signal into
Yeah.
small functions.
This is called the fast Fourier transform. But if you want to take all of the signal, you take all of it. So the transform takes it from one domain into another. The series just represent it as a series of functions that are summed together, and then you have this one really equals to this function. This is really like amazing to think about it, that it's not approximately like this one. It equals by infinity. They are equal to each one. So this is the Fourier series. This is like a really heavy mathematical idea. But now we want to take it into something which is more practical, and then we don't care about all of this calculation. We just want to understand what does the computer give us when we ask him perform the Fourier transform of blah, blah, blah. So what he does, he takes the signal from this domain and he presents it at the frequency domain. And they are, of course, connected. It's a good question because they are connected to each other. But the transform is just changes between different domains.
It doesn't take all the, if I understand correctly, it doesn't take all the sine and cosine function until infinity.
Right.
But
You might have it like until infinity, but you represent them like this, like delta functions, or by a function in the frequency domain that relates them. Okay.
Yeah,
Right.
then can I have a question about the thing you just explained?
You had a question, Amit?
Yeah, so about what you just said, so when I aspire to the infinity, I give it less weight to the function. I mean, the delta function is becoming more less affects the calculation.
The delta function, yes, it might be so, Amit.
So as long as I go to the infinity, it's less. I mean, it's less affect my function. It's the weight is more. It's more less. כאילו המשקל של זה פחות גבוה על החישוב של
The
הפונקציה.
weight is lower. Yeah, it depends on your signal. For example, in a white noise, you have the same weight, ideally, from 0 to infinity. You have the same weight, almost the same weight for all the possible frequencies.
Okay, thank you.
Okay. I hope it was helpful, and I may the force be with you tomorrow.
We only split the signals into the frequencies, and that's what we do.
This is what the Fourier transform does, yes. It's kind of finds the frequencies and their weight on your signal, in your signal. Okay.
Week three, this week.
I gave it until the 8th of July, yeah. And for the last project, it is until the 21st of July, and it will be published really this week. And if someone will need some more time, you can, probably will give you some more time, but I don't want it to take it too much longer because I want you also to have enough time to prepare to the last quizzes of the course.
Last quiz.
Last quiz of the course, which I believe that will be